Good morning, afternoon, or evening, depending on which part of the world you're tuning in from. Today, I'm excited to share with you our work on out-of-distribution detection with language models. This is joint work with my advisors, Jinjie Hu and Sharon Lee. Despite recent successes, many pre-trained language models are still fragile under distribution shift, making their applications to the real world challenging. The problem of out-of-distribution or OOD detection addresses the identification of anomalous data, enabling the model to abstain from prediction when required. This is especially important for high-risk settings like healthcare and finance, where unreliable predictions could incur great costs. To concretize things, let's run through a quick example. To start off, we assume access to both a pre-trained model and a dataset for the intended downstream task, which we call the in-distribution or ID data. Our first step would be to fine-tune the model to this downstream data. With only this, we can now safely deploy our model. The reason for this is because every new data point encountered during inference must first meet the OOD detector. The detector almost works like a filter, dropping points it deems OOD while only allowing the ID points to the model for prediction. Now let's look at the detector in a little more detail. Distance-based OOD detection is a simple but powerful class of detection methods, and nearest neighbors is one such state-of-the-art method. We start off by using the data representations from the penultimate layer of the model. When visualized, we can see these data points forming clusters. Loosely, each cluster contains all the ID points for a specific class in the downstream classification task. Given two query data points, shown as triangles here, the OOD detector simply measures the distance to their nearest neighbors in the ID data. This distance has been shown with dotted lines. With the green point, the distance is below a specified threshold, so the point is classified as being ID. The red point is too far from any ID training point and is thus classified as OOD. An underlying assumption in both our example and most detection methods is that the fine-tuned model produces embeddings customized to the ID data, which would somehow be more useful for OOD detection. But is this really true? Despite its common use, the understanding of the role of fine-tuning and its necessity for OOD detection is largely lacking. Is fine-tuning necessary at all for OOD detection? To answer this question, we introduce a setup of zero-shot OOD detection. Like before, we have access to a pre-trained model and a dataset. However, unlike before, we skip the step of fine-tuning on the ID data and feed the data embeddings of the pre-trained model directly to the OOD detector. There is no training involved in this pipeline, and the detector itself has no learned weights, so we label this setting as zero-shot. We compare our zero-shot approach to fine-tuning with three popular objectives. We also use two powerful distance-based detection methods in our experiments. Lo and behold, zero-shot OOD detection has almost near perfect performance using a pre-trained Roberta model. Furthermore, this approach outperforms fine-tuning with various popular objectives. While this is very promising, why is zero-shot OOD detection so good? Visualizing the data from the penultimate layer of the model helps shed some light on this phenomenon. In the left figure, we observe that pre-trained language models create separated domain clusters of sentence embeddings per ID and OOD data. Here the ID data has been shown in red. The strong separation of these clusters boosts the performance of distance-based detection. In contrast, fine-tuning, shown on the right, induces a model to divide the single domain cluster into multiple class clusters matching the downstream task. When a fine-tuned model encounters an OOD data point, it attempts to classify it by mapping it to one of the existing ID clusters. However, due to the distributional difference of the data point, the model is unable to perfectly map such a point, and OOD's points end up in the space between ID class clusters most similar to it. Fine-tuned representations of the data thus make distance-based detection more challenging. Consider this talk a teaser to our main paper. Please stop by our poster or reach out if you want to know more about the best way to fine-tune a model if you want a single model for OOD detection and downstream classification. Or maybe want a deeper understanding of how fine-tuning plays a role in impacting embeddings for OOD detection, or understanding how different detection methods compare under various fine-tuning regimes. Thank you for your time. Please do check out our paper and feel free to reach out. We look forward to some interesting discussions.